In this section, instead of dealing with a generic linear map, we deal with an endomorphism, which is a linear map between a vector space and itself. The motivation is twofold. Firstly, these kind of transformations appear very often in mathematics and its applications. Secondly, as we're going to see, an endomorphism has stronger properties than those of a generic linear map, which are very useful to solve interesting problems. To fix the notation, let's take two endomorphisms, f and g, on the vector space V of dimension n, and their associated matrices A and B respectively with respect to any choice of basis of V. These matrices are square matrices of dimension or order n, which means that they have exactly n rows and columns. The space in which they live is indicated with this symbol here. So instead of repeating 2 times n, which is useless, we just write n here. For square matrices, it makes sense to define their diagonal, which is composed by the elements of the type AJJ. So the diagonal of A will be A11, A22, etc., etc., ANN. For any two square matrices of order n, we can write their product A times B or B times A. In fact, in this case, the inner dimensions always match. Since Mn of f is a vector space, it makes sense to ask ourselves what is the null element of this vector space. Well, it is the zero matrix, that is, the matrix with all zero entries. Of course, it represents the null linear map, which is the linear map that takes every vector of V into the null vector of the vector space. The unit element of Mn of f with respect to the operation of matrix product is the so-called identity matrix. As you can see here, the identity matrix is a special type of diagonal matrix which has all zero entries except in the diagonal, in which the entries are 1. It's very easy to see that En is the matrix representation of the identity map. To see that, write as a column vector the components of every vector of V and perform the matrix product between the identity matrix and this column vector here. Using the rules of rows times columns product, you can see that what you find is exactly the original vector. More generally, if you have a scalar lambda belonging to the field F, you can obtain from the identity matrix the so-called scalar matrix, which is nothing but lambda times the identity matrix. So you find again a diagonal matrix with all lambda on the diagonal and 0 outside. Using the same argument as before, it's easy to prove that lambda times En represents the endomorphism f of V equals lambda times V. These kind of transformations play a crucial role in linear algebra, as you will see when you study the eigenvalues and eigenvectors of a linear map. Having all values 1 or all values lambda on the diagonal is a very special condition. In general, we define a diagonal matrix as a matrix with all zero entries except A11, ANN, which can be different on the diagonal. As an example, a diagonal matrix of order 3 is given by 1, 2, 1, and 0 outside the diagonal, like this. Diagonal and scalar matrices have particular properties regarding the commutativity of product. Let me recall that two matrices are said to commute if AB is equal to BA. The first property is that the identity matrix and all scalar matrices commute with all the other matrices, of course, with the same order. Then it can be checked that any two diagonal matrices commute with each other. However, pay attention, it is not true that diagonal matrices commute with any other matrix. Here's an example. You have this diagonal matrix here, and you multiply it, for example, on the left by this matrix here. What you obtain is the matrix written here. Try to multiply this diagonal matrix on the right by the same matrix that you have used to multiply on the left. What you obtain is this matrix here, and as you can see, the result is different. So, in general, A times D and D times A is not the same whenever A is not a diagonal matrix. Another specialty of square matrices is that they can exhibit a triangular shape. Let's see what it means. For obvious reasons, if the only non-null elements of A are those contained in its diagonal and in the entries above, then we say that A is upper triangular. Similarly, if the only non-zero elements of A are those contained in the diagonal and below it, we say that A is lower triangular. Let's now pass to the important concept of divisor of zero. To introduce this concept, we must first recall the cancellation law, which holds in R and C. This law says that if you multiply together two real or complex numbers and you obtain 0, this means that either A or B or both of them are 0. This is not true anymore for matrices. In fact, you can have two matrices which are non-null and multiplied together, they give the null matrix. Here's an example. This matrix and this matrix are not the null matrix, however, multiplied together, they give rise to the null matrix. This peculiar feature gives us the possibility to define two non-null matrices A and B, divisors of 0, if their matrix product gives rise to the null matrix. Let me tell you that we can also obtain the null matrix by multiplying a non-zero matrix with itself a certain number of times. More precisely, we say that a non-zero matrix A is a nilpotent of order R if the power R of the matrix is the null matrix. Here you have an example of a nilpotent matrix of order 3. In fact, the matrix A is non-null. Then you have A square, which is A times A, which is this matrix here. And then you have A cube, which is A times A times A, which is the null matrix. Let's now introduce the paramount important concept of inversion of a matrix, which makes sense only for square matrices. First of all, it's important for you to recall that it makes sense to talk about the inversion of a matrix only for square matrices. To introduce the concept of inversion of a matrix, let's first recall what happens in R. If you have a non-zero real number A, then the inverse of A is the real number B such that AB equals BA equals 1. And in this case, we write B in this way. If we want to transpose this definition in the matrix realm, we have everything we need. In fact, we know how to multiply matrices, and we know what is the unit in the matrix realm, that is, the identity matrix. For this reason, we say that a matrix B is the inverse of a non-null matrix A if AB or BA is equal to the identity matrix. And we write this symbol here. However, differently from what happens in R, the fact that A is a non-null matrix is not enough to guarantee the existence of its inverse matrix. The reason is actually very easy to understand. In fact, we know that every square matrix can be represented as the matrix associated to an endomorphism, and we know that an endomorphism is invertible if and only if it is an isomorphism. So, if A is the matrix representation of an endomorphism which is not one-to-one or onto or neither of them, then A cannot be invertible. Divisors of zero represents a class of square matrices that cannot be inverted. In fact, if A and B are two divisors of zero, then it means that they are non-null matrices, keep in mind this, such that A times B is equal to the null matrix. Suppose now that it exists the inverse of A, such that the inverse of A times A is equal to the identity matrix. Then look what happens. We can rewrite the matrix B as the identity matrix times B. But the identity matrix can be decomposed like this, okay? And so, using the associativity of the matrix product, we can write the parentheses here, and we have the inverse of A times A times B. However, recall that A times B is the null matrix, and so we have the inverse of A times the null matrix, which gives the null matrix. This proves that if it exists the inverse of A, then B is the null matrix. However, this is in contradiction with the fact that B cannot be the null matrix, and so it's impossible. If we exchange the role of A and B in the previous argument, we prove that also B cannot be invertible. Let me pass to the final definitions of this section. An endomorphism, which is also an isomorphism, is called automorphism. The vector space of all the automorphisms of a vector space V is denoted with this symbol here, and the matrices associated to these automorphisms are exactly the invertible matrices. There is a particular symbol for the vector space of invertible matrices of order n, and this symbol is this one here, and it's called the general linear group of order n. Thanks to the nullity plus rank theorem for matrices that we have discussed in the previous lesson, we have that a square matrices of order n belongs to the general linear group of order n if and only if it is full rank. There is another condition that characterizes all invertible matrices of order n, and it is the fact that their determinant is different than zero. The concept of determinant of a square matrix has a huge importance in linear algebra and its applications. We are going to introduce it and analyze it thoroughly in the next section.
It's now the time to recap the most important properties of endomorphisms and their relations with square matrices. First of all, recall that an endomorphism is by definition a linear map between a vector space and itself. The vector space of all the endomorphisms of V is denoted with this symbol, and recall that an endomorphism is associated with a square matrix, that is, a matrix with the same number of columns and rows. The corresponding vector space of these matrices is written like this, where n denotes the dimension of the matrix and f denotes the field from which we gather the scalars that appear in the matrix. In general, working with square matrices associated with endomorphisms is easier than working with rectangular matrices associated to generic linear maps. In fact, the product of two square matrices is always defined, because in this case the internal dimensions are of course always the same. Moreover, when we deal with a square matrix, we can also define its inverse. The inverse of A is the matrix A minus 1 that, multiplied by A on the left and on the right, gives rise to the identity matrix of dimension n. However, pay attention, the fact that for every square matrix we can define the concept of its inverse doesn't mean that the matrix is indeed invertible. A test of inversibility for a square matrix is actually given by another quantity that we can define only for square matrices, the determinant. The determinant has a huge importance in linear algebra, and we will see it in action in chapter 3.
The determinant of a square matrix A of order n with entries in the field F is a scalar that belongs to F, which is written either like this or like this. In mathematical books, the determinant is defined through a very general and abstract formula which permits to prove the properties of the determinant quite easily. However, in this course, we don't have the time to see those proofs, and so it doesn't make sense to use our time to introduce the most general definition of determinant, considering also the fact that it's computationally useless. In fact, if we translate the formula into an algorithm to be run by a computer in order to calculate the determinant of a matrix of order 30, which is not that big of a matrix, we will need 10,000 times the age of the universe in order to complete the computation. This is the reason why I chose to introduce the determinant using a more computationally efficient formula due to the French mathematician Laplace. In Laplace's formula for the determinant, there appear some concepts that I introduce in this definition here. Consider a square matrix A of order n. We write with Aij the square matrix of order n minus 1 obtained from A by removing the ith row and the jth column. Let's consider immediately an example. Consider this matrix of order 3. Then this matrix will be a matrix of order 2 obtained from A by removing the second row and the third column. So A23 will be what remains, that is, the matrix whose entries are these ones here. The determinant of this smaller matrix is called the ijth minor of the matrix A. If the matrix Aij is a scalar, then its determinant is defined by the scalar itself. If we multiply the ij minor of the matrix A by -1 to the power I plus j, then we obtain the cofactor of the element Aij of the matrix A. The matrix whose entries are the cofactors of the elements of A is called the cofactor matrix, and it's indicated with the letter C. I'm perfectly aware of the fact that these definitions come out of the blue. The only way to justify them is by introducing Laplace's theorem, which can be stated in a much simpler way thanks to these definitions. Monsieur Laplace discovered that there are two equivalent ways to compute the determinant of a square matrix. The first one is called development along a row, and the second one is called development along a column. The Laplace development along the row I is obtained by first computing the cofactors of the entries of the ith row of A, here they are, then by multiplying the cofactors by the corresponding entries, here they are, and finally by adding together all these scalars. Here's the sum. As you can see, the Laplace development along the column J is analogous. Of course, we are immediately going to see examples of computations of the determinant through the Laplace developments. But before, let me point out the golden rule for the proper application of the Laplace formulas. It's clear that if one entry of the matrix A is 0, then this entry will not contribute to the sum, because the corresponding term will be null. Hence, remember that it is convenient to perform the Laplace development along those rows and columns which have the largest amount of zero entries. A square matrix of order 1 is simply a scalar, and its determinant is the scalar itself. So the first non-trivial example that we analyze is a square matrix of order 2. Since n in this case is 2, the formula that we need to use is this one. If we choose, for example, to develop the determinant along the first row, then I becomes 1 in all the places in the formula, like this. If instead of writing the compact notation for the sum, you write it explicitly, you find this expression here. This coefficient is minus 1 to the power 2, and so it is 1. Instead, this coefficient is minus 1 to the power 3, which is minus 1. Recall now that this is the minor 1, 1. That is the determinant of the matrix of size 2 minus 1 times 2 minus 1, that is 1 times 1, which is just a scalar, obtained by the matrix A by deleting the first row and the first column. So if we delete the first column and the first row, we end up having just A to 2. So the minor 1, 1 is the entry A to 2 of the matrix A. Similarly, in order to obtain the minor 1, 2, we have to erase the first row and the second column. So what's left is the entry A to 1. Hence, the minor 1, 2 will be A to 1. Replacing all the values that we have explicitly obtained in the formula for the determinant, we obtain this formula here. So we have found that the determinant of a square matrix of order 2 is very simple to obtain. That is, we have to multiply together the elements of the diagonal, like this, and then we have to subtract the product of the off-diagonal elements, like this. If you want a numerical example, consider this matrix here, then you can repeat the computations that are written here, and you will find that the determinant is 4. Let's now see how we can use the formula of Laplace in order to compute the determinant of a matrix of order 3. This time I chose to develop the determinant along the first column. The corresponding formula is this one here, with 1 instead of j. And since we have a square matrix of order 3, we have to write 3 instead of n. As before, if we write explicitly this sum, we obtain this formula here. This time the computation of the minors is not so immediate as before. So, for example, let's compute the minor A11. The minor A11 is by definition the determinant of the submatrix obtained from A by erasing the first row and the first column, like this. As you see, the matrix that you obtain is this one here, and if you want to compute the determinant of this matrix, you can use the formula that we have computed in the first step, and so it will be A22 times A33 minus A23 times A32. Now the minor A21 is by definition the determinant of the matrix obtained by erasing the second row, like this, and the first column. And in fact, this is the submatrix of A that you find written here. Finally, The minor A31 is the determinant of the submatrix obtained by erasing the third row and the first column of A. And so this is the submatrix of order 2 that you find written here. If you introduce the explicit expressions of the minors in this formula and you take into account the signs written here, you find this formula here for the determinant of a 3 by 3 matrix. Let's see this formula in action using an explicit matrix, this one here. Remember that the first thing that you have to keep in mind when you compute the determinant is the golden rule to apply Laplace formula, which says that we have to choose for the development of the determinant the row or the column with the largest amount of zeros. In this case, we can choose to develop the determinant either along the third row or the third column. It's up to us. I chose the third row, and we just have one term, the one related to the coefficient -2. So we have to write -2 times -1 elevated to the sum of the indices of this entry, and the indices of this entry are 3 because this is the third row, and 2 because this is the second column. So we have -1 to the power 3 plus 2. Finally, we have to multiply all this by the minor of order 3, 2 of the matrix. So we have to erase the third row and the second column, remaining with this submatrix of order 2. Now let's pass to the computations. We have -1 elevated to 5, and since 5 is an odd number, -5 elevated to 5 is -1. However, -1 times -2 is 2. And so we have that the determinant of A is 2 times this minor here, and we have already seen that this minor is nothing but the determinant of this submatrix. The determinant is -1 times 1, which is -1, minus 0 times 3, which is 0. So the final step gives 2 times -1, -2. Let's check that we can develop the determinant along any rows and columns, and we will always get the same result for the determinant by developing the determinant of A along the third column, this one here. The only non-zero entry of the third column is 1, and so we write 1 here, and then we have to multiply it by -1 to the power 2 plus 3, because 1 belongs to the second row and the third column. Finally, we have to compute the minor A23. This is the determinant of the submatrix obtained by erasing the second row and the third column, that is, this matrix here. So we have a -1 that multiplies the determinant of this matrix, and by computing the determinant, we have again -2. So you see that when you repeat a certain number of times the computation of the determinant of a matrix, it becomes a quite automatic procedure. It can be long if the matrix is big, but it's not complicated at all. Let's increase a little bit more the difficulty of the computation of the determinant by considering this square matrix of order 4. Using the golden rule, we can develop the determinant using Laplace formula, either choosing the third row or the fourth column. I chose in a totally arbitrary way the third row. Using exactly the same strategy that I showed you before, you have that the determinant is written like this. The greater difficulty consists in the fact that these two minors are determinants of matrices of order 3. As a very useful exercise, you can check that these two determinants are 7 and -23 respectively. Introducing these values here and here, you find that the determinant of the matrix A of order 4 is 55. After these examples, it should be clear that for square matrices of order larger than 2, the computation of the determinant becomes an iterative procedure in which we have to compute determinants of square submatrices of decreasing order until arrive to a one-by-one matrix which coincides with a scalar. Moreover, from the previous examples, it should be clear that the signs to put in front of the minors in order to create the cofactors have a regular pattern. For the square matrix of order 4 that we have just considered, the pattern is this one. Nobody with a common sense will ever ask you to compute by hand the determinant of a square matrix of order larger than 4. For that, you can use computers. But if you are in the middle of the jungle without a computer and you need to calculate by hand the determinant of a square matrix of order larger than 4, well, keep in mind this pattern and extend it naturally. Now that we have defined the determinant of a square matrix and how to compute it, let's see why this concept is so important in linear algebra. Take any endomorphism F on the vector space V, then we know that F is invertible if and only if the matrix A associated to it with respect to any choice of basis of V is invertible. The theorem says that this happens if and only if the determinant of A is different than 0. Since square matrices are invertible if and only if they are full rank, from the previous theorem it follows that a square matrix is full rank if and only if its determinant is different than 0. So you see that whenever you find a square matrix which has a determinant different than 0, this matrix is associated with an isomorphism. The determinant has a bunch of properties. In the following theorem, we collect the most important of them that will be useful in order to solve linear systems in Chapter 3. Let's consider two square matrices A and B of dimension n and two scalars lambda and mu. Then the first property of the determinant is that the determinant of A is equal to the determinant of the transpose of A. Swapping rows and columns doesn't change the determinant. The second property is that if A is either a diagonal or a triangular matrix, upper or lower is not important, then the determinant of A is simply the product of the diagonal elements of A. Then we have that the determinant of lambda times A is equal to lambda to the power n times the determinant of A. That is, the dimension of the square matrix n becomes the exponent of the coefficient lambda. For this reason, the determinant is not a linear function of matrices. For example, if you have a matrix of dimension 2 over the reals, then if you consider the determinant of lambda times A, what you get is lambda squared times the determinant of A. This property tells us that the determinant is not a linear function of matrices because it is not homogeneous. Remember that homogeneity means that we can take off this coefficient without any exponent. What about additivity? What we can say is that in general, the determinant of A plus B is different than the determinant of A plus the determinant of B. So in general, additivity doesn't hold. However, there are a couple of matrices A and B for which this equality holds. What this statement says is that we can always find a couple of matrices for which the function determinant is not an additive one. So to resume, property 3 says that the determinant is not a linear function of the whole matrix. However, property 4 says that the determinant behaves linearly when it is considered row-wise or column-wise. Let's see what it means. If the generic kth row Rk of A can be written as lambda times R prime plus mu times R second, where R prime and R second are two row vectors, then the determinant follows this behavior. The determinant of A, where Rk is written as this linear combination of row vectors, is equal to the linear combination of the determinant of the matrices that have, instead of row k, the row vector R prime and R second. This is the precise meaning of row-wise linearity. As you can imagine, column-wise linearity is defined in an analogous way, which means that if we consider the generic kth column as this linear combination, where C prime and C second are two column vectors of Fn, then the determinant of A has this column-wise linear behavior. We will see an exercise to better understand this property. Let's now pass to the following property. We have that if the matrix B is obtained by the matrix A by exchanging either two rows or two columns, then we have that the determinant of B is equal to minus the determinant of A. Property 5 implies property 6, that is, if A has two identical rows or two identical columns, then the determinant of A is 0. In fact, if we exchange the identical rows or the identical columns, the matrix remains the same. However, its determinant switches sign, which means that the determinant of A must be equal to minus the determinant of A, and this is possible if and only if the determinant of A is 0. The following property is that if A has at least a null row or a null column, then its determinant is 0. Now we discuss a property of the determinant that we will use all the time in chapter 3 when we will deal with systems of linear equations. The determinant of A doesn't change if we sum to a row a linear combination of the remaining ones. Let's see what it means. Write the matrix A row-wise and fix your attention to the row Ri. The theorem says that if we consider another matrix A prime, which has instead of the row Ri, the row Ri prime that we are going to construct, then these two matrices have exactly the same determinant. The row Ri prime is built by adding to the row Ri a linear combination of the other row vectors. As you can see, here we have the other row vectors, here we have generic scalars, but what is important is that the index k of the other row vectors ranges from 1 to n except for the index I, that we have fixed. So this is a linear combination of the remaining row vectors except for the row vector Ri, okay? Because we have eliminated this possibility. To have a concrete example at hand, consider this matrix written row-wise and fix your attention to the row R2. We have replaced in the matrix A prime the row R2 with the sum of R2 and a linear combination of R1 and R3, which are the remaining rows in this case. Then this property says that the determinant of the original matrix and this novel one are exactly the same. As I told you, we will use this property many times during chapter 3. I explained in detail what this property means for rows, but as you can see here, this property holds also for columns. Let's continue with the final properties. If A has at least two linearly independent rows or two linearly independent columns, then the determinant of A is 0. Next property deals with the product of matrices. We know that this operation is always well defined for square matrices, so we can ask ourselves what happens when we consider the determinant of the product of A and B. Well, Binet's theorem says that the determinant factorizes in the product of the determinant of A and the determinant of B. In the next property, we suppose that the matrix A is invertible. Then the determinant of the inverse of A is precisely the inverse of the determinant of A. Finally, we have a very important feature of matrices, that is, if B is an invertible matrix, we have that the determinant of the matrix B times A times B minus 1 is equal to the determinant of A. This operation is called conjugation of the matrix A by the matrix B. So, this formula says that the determinant is invariant under conjugation. We have finished the discussion of the properties of the determinant. However, property 12 gives me the opportunity to introduce another extremely important function defined on matrices. Suppose that A is a square function of dimension n, then its trace is the sum of all the diagonal elements of A, that is, A11 plus A22, etc., A and n. Property 12 holds also for the trace, which means that if we conjugate A with an invertible matrix B, then the trace of the conjugation is exactly the same as the trace of the original matrix. The crucial importance of this formula and this formula will be discussed in the course of Euclidean spaces. Before introducing the concept of inverse matrix, we need a preliminary definition, that of adjugate matrix. Given a square matrix A of dimension n, we call its adjugate matrix, and we indicate it with this symbol here, the transpose of the cofactor matrix of A. The abstract definition of adjugate matrix is written here. However, I prefer to introduce it with a concrete example of a square matrix of order 2. To build the cofactor matrix C, we need all the minors of A, so this one, this one, this one, and this one, multiplied by the signs that are contained in this matrix here that we have already seen. And so here we have plus, minus, minus, and plus. Of course, we avoid writing plus here and here, and we can pass to the computation of the minors. The minor A11 is the determinant of the submatrix obtained by erasing the first row and the first column of A, and so it's the determinant of A22, but since this is a scalar, it's just this scalar here. So we can write A11 equal A22. Then for the minor A12, we have to erase the first row and the second column, and we remain with A21, and so the minor A12 will be A21. Similarly, we find the minor A21 to be A12, and the minor A22 to be A11. As you see, if you introduce these explicit values of the minors into the cofactor matrix C, you find the matrix written here. The adjugate is simply the transpose of C, and so you have this matrix here. If instead of writing the double index, you write A, B, and C for the entries of a matrix, you obtain that the adjugate of A is written like this. Now, once you have found the adjugate of a matrix, the computation of its inverse is very easy. In fact, if you have an invertible matrix of order n, that is, its determinant is different than 0, the inverse of A is given by the adjugate of A divided by its determinant. Let me tell you immediately that the computation of the inverse of a matrix is a very time-consuming operation. Nowadays, we just perform it with computers. However, even with computers, recall that whenever it's possible, it's better to avoid performing inversions of large matrices and use different strategies. In order to test all the things that we have said, I leave you as an exercise the computation of the inverse of this matrix here. I strongly invite you to perform the computations by yourself and then to check the results using the computations that I wrote in the notes. In Chapter 3, we're going to examine the usefulness of matrices for the solution of systems of linear equations. However, already in this chapter, we can discuss the usefulness of matrices in the field of cryptography. As you know, if you want to send a secret message to someone, you have to modify its content in order to be readable just by the receiver. In order to do that, in general, the first thing we do is to codify letters with numbers. Since the English alphabet is composed by 26 letters, the integer numbers that we're going to discuss are those contained between 0 and 25. The association between letters and numbers in alphabetical order is A is associated to 0, B to 1, etc., etc. Z is associated to 25. Even one of the easiest encryption algorithms, for example, adding a constant to the integer number associated to a letter, for example, 3, shows that we have to face a problem. The problem starts when we arrive to the number 23. In fact, if we sum 3 to 23, we get 26, which is strictly larger than 25, and so we are outside the range 0-25. The classical solution to remedy this problem is called cyclic extension and is depicted in this diagram here. With the encryption n plus 3, the cyclic extension is this simple rule. Divide n plus 3 by 26, and the remainder of the division will be the cyclic extension. Let's see some example. Let's start with the first letter which creates problem, x, which has position 23, plus 3 is 26, and 26 can be written as 1 times 26 plus 0. 0 then is the remainder of this division, and so the cyclic extension of x is 0. If you repeat this same argument on y, you will find that the remainder of this division is 1, and so the cyclic extension of y will be 1. Similarly, for z, its cyclic extension will be 2. Now, using the encryption rule m+3 with the cyclic extension, you find that the encryption of the word hello is this one here. In fact, the codification in alphabetical ordering of hello is this string of numbers that you see here. You add 3 and you find this other string that is written as core. Now, if your friend, the receiver, knows the encryption code, also called the key, then he or she knows how to reconstruct the original word. In fact, it is enough to undo the original key by performing k goes to k minus 3, possibly together with the cyclic extension. As you can understand, this is a very, very basic encryption technique. It is very easy to crack the code, and so your secrets will not be safe anymore. Nowadays, the standard encryption techniques uses the decomposition of a very large number into the product of prime numbers. This is an operation that even a supercomputer can do in a huge amount of time. We are not going to discuss this encryption technique because it's quite complicated. Instead, we discuss a sort of intermediate one, which has the advantage of showing the usefulness of matrices. We consider again the basic encryption algorithm discussed before, but this time we don't apply it to single letters, but to couple of consecutive letters in a word. If it happens that a word is composed by an odd number of letters, as for example hello, then we form a couple with the last letter that remained alone by coupling it with z. So instead of considering the word hello, we consider this string of couple of letters. Using the encryption rule n goes to n+3, we obtain again the same numbers that we have found before, plus the number 2, which encodes z. Now, the reason why we take couples is that we can arrange a couple of numbers into column vectors like x1, x2, and x3 that you see here. The fact of having the possibility to deal with column vectors allows us to introduce the core of this encryption method, that is, a matrix. For reasons that will become clear very soon, we need to consider an invertible matrix like this one, whose inverse is indicated here. Having at disposal column vectors and a matrix, what we can naturally do is to operate the matrix multiplication, obtaining new vectors that I have indicated with tilde. As you can see here and here, through matrix multiplication, it can happen that you go outside the admissible range of integers. So what you do is to apply the cyclic extension to get back these numbers into the admissible range. So now what you have are these 3 column vectors, and you can alphabetically associate them to this word here. Now you send this word to your friend, and imagine that you have communicated to your friend only the encryption technique n goes to n+3 and the matrix M. What your friend will do is to extract these vectors from these couples, like this, and apply to all of them the inverse of the matrix M. Why that? Well, you have to remember that we have defined x tilde of j as m applied to xj. So, if we apply m minus 1 to x tilde j, we have m minus 1 times m times xj. But m minus 1 times m is the identity matrix 2 by 2. And so we know that this matrix product is exactly xj. So your friend will recover the original couples that you have sent, and thanks to the fact that you have communicated also the encryption code, he or she can decode what you have sent and come back to the original word. Notice that in order to crack the previous encryption method, this one here, we just needed to know one number, 3. In this case, instead, we need to know 4 numbers, those in the matrix M, and also, and importantly, their position in the matrix, which of course adds a further level of complexity. This encryption method based on matrices becomes safer and safer as the dimension of the matrix grows, because in this case the number of permutations of the positions in the matrix entries becomes really large, and so it will take quite a long time to find out the correct encryption matrix.